Hello and welcome back to Calculus. First, as always, I want to thank all the nice people that support this channel by liking and subscribing. In today's part 33, I'd like to go over how to solve differential equations in exact form. This, surprisingly, will require the product rule for differentiation. So first, let's go over what an exact differential equation is. It has the following format, where on the left-hand side, you have the derivative of two functions multiplied equals to one function. This is easy to solve because when we take the integral from both sides, on the left-hand side, the derivative and the integral simply cancel each other out. And on the right-hand side, most of the time, it's just going to be a standard, easily solvable integral. However, most differential equations are not an exact form. So that means our goal is to put it into the exact form by multiplying the differential equation by something. So let's first figure out what that thing is going to be. We first begin with a common format for differential equations called the standard form. And it looks like the following. You have dy over dx plus a function of xp times y is equal to q of x. In this case, p and q are both functions of x. Now, even if your differential equation doesn't look like this format, most of the time you can just move things around or perhaps divide everything by something to make it into the standard form. Now, as a refresher, please recall the product rule for differentiation, which states if we are doing the derivative of two functions u and v multiplied together, the derivative is going to be du over dx times the original v plus dv over dx times the original u. Now let's take our differential equation in standard form and compare it to the derivative. You can see that we have to multiply the left-hand side of the differential equation by another function so that the left side becomes the derivative of a product. So let's call that function that we have to multiply mu of x. So we multiply our differential equation in standard form by mu of x, and our goal is to make it into the derivative of the product of mu of x times the y function. So the derivative of a product. Hence, the product rule for differentiation is stated right here. Now let's apply the product rule for the right-hand side and also open the parentheses on the left-hand side. I open the parentheses on the left-hand side and apply the product rule on the right-hand side. And as you can see, here on the left and here on the right, we have the same things. So that means we can simply cancel them out. We're left with just this, and also y can also be cancelled out on both sides. And this just leaves mu x times p of x equals to d mu over dx. This technically is a differential equation, which we can easily solve by using separation of variables. So our goal would be to move the mu's to the right-hand side and the x's on the right-hand side, on the left-hand side. And now that we have separated these variables, we can take the integral from both sides. On the left, the integral just stays because we do not know the function p. On the right-hand side, however, what we get is the natural log of our mu of x function. For now, I'm going to exclude the plus c, simply because we're trying to get an arbitrary result and not a specific one. And now please don't get lost. Our goal was to figure out what this mu of x is going to be so that we can multiply both sides of the differential equation to make it into the product rule. So that means my end goal here is to write mu of x in terms of something. And this can be done by getting rid of the natural log and writing e raised to the power of the integral of p of x dx. And this result that we get here, ladies and gentlemen, is the function mu that we need to multiply on both sides of the differential equation to make it into the derivative of a product. And this mu function has its special name. It's called the integrating factor. So now that we have figured out the theory behind solving differential equations in standard form, let's take a look at a specific example. Here we have a differential equation, and please recall that we need to put it into standard form. Here it is not that difficult to deal with. All we have to do is divide this entire differential equation by x plus 1. After division, you can see that our differential equation is now in standard form. And next, we need to multiply this by some integrating factor. So that means I need to identify what my p of x is going to be. In our case, that would be the 3 divided by x plus 1. And if you notice something wrong, you're probably right, because more specifically, it is the negative 3 over x plus 1. In standard form, this here is a plus sign. So if it's a minus, we take that into p also. This means we can now find the integrating factor that I'm going to denote with I, and that is simply equal to e to the power of the integral negative 3 over x plus 1 dx. This integral up here is easily solvable. It is simply going to be the negative 3 times ln of x plus 1. And if you know some rules about logs and exponents, you can probably see that this can be simplified to x plus 1 raised to the power of negative 3, or rewritten as 1 over x plus 1 to the power of 3. This means that now I need to multiply the differential equation in standard form by our integrating factor. This is actually quite nice because on the right-hand side, the powers cancel out and all we have left is x plus 1. On the left-hand side, however, we can open the parentheses and some things might also cancel out. So what we get is 1 over x plus 1 to the power of 3 dy dx minus 3 over x plus 1 to the power of 4 times y equals to x plus 1. The left-hand side now has become a product rule. If you can spot this, here we can set this as the u function. So that means here is going to be the u prime. Consequently, this here is going to be the v function and this is the v prime. Now you might say, well, the product rule has a plus sign. But please note, the v function is 1 over x plus 1 to the power of 3, which rewritten is x plus 1 to the power of negative 3, which means when we do the derivative of it, the negative goes into the front, and hence our product is going to become a negative 1. So technically that means on the left-hand side, I can rewrite this in a more compact way. I can write it as the derivative of the u function multiplied by the v function. So in our case, that would be y multiplied by 1 divided by x plus 1 to the power of 3. At this point, you can simply integrate both sides. And since on the left-hand side, the integral and the derivative cancel each other out, what you have is y over x plus 1 raised to the power of 3. And on the right-hand side, it's going to be an easy integral using the power rule, which you get x squared over 2 plus x and plus c. And finally, y is going to be equal to the entire right-hand side multiplied by x plus 1 raised to the power of 3. And here we have solved this differential equation which was originally in standard form. So please remember that we need to multiply a differential equation by another function called the integrating factor, which I showed how we got, and then we turn it into the derivative of a product, which can be rewritten in a more simple way, and then the integral is going to be easy to solve on both sides. So this is it for now. In the next video, I will show you a numerical way to approximate the value of a differential equation at specific values. So I really hope to see you there, and have a nice day. Bye.